This video picks up where we left off on the review yesterday. So the question is, potential difference is, number one, difference of amount of charge between two places. Number two, another word for voltage. It is the difference in electric potential energy from one place in a circuit to another. Number three, difference in the rate of flow of current from one place to another when the circuit is flowing faster in one part of the circuit and slower in another part of the circuit. Or number four is abbreviated PD and is measured in potential. Okay, your answers. All right, last check for answers. So the answer to the question is number two. Number two is the correct answer. I'll put it up here so we can see it. This is the definition. Potential difference is a synonym for voltage. That is the difference in the electrical potential energy between two places in our circuit. And that was a definition that we needed to know. And we had used the example in fluid, like we have a pipe and water won't flow unless we have a higher gravitational potential energy in this section of the pipe, and then it would flow down. If we had a flat pipe, then we would have no water flow. If we don't have more potential energy, electrical potential energy at one side of the circuit, then no charge will kind of be pushed through to the other side of the circuit. Okay, what is the formula used for Ohm's law? And what do the symbols stand for? 1, E equals Q over R. 2, R equals I, V. 3, V equals E over Q. And 4, V equals IR. Take a second to look also at what these symbols are stand for. Okay, answers? Okay, last call for answers. Okay, so the correct answer is number 4. We provide the triangle on the test, and the triangles, remember, oh, that one's not up on the sidewall, but I will have it up for you before tomorrow. But we provide the triangles. The V would be in the top of the triangle. And let me just draw it right here for you. The V would be in the top of the triangle, standing for voltage. The I stands for current, measured in amperes, remember, and R stands for resistance. And recall, using the triangle, if we cover up the V, then the letters are beside each other, so they get multiplied. I, current, times resistance. This one should make no sense because V does not clearly stand for resistance. So that should have helped you eliminate this one. As I said, you'll be given the triangle, so you should be in good shape. All right, next question. All right, it says circle all of the materials that make a good electrical conductor. So take a moment and on your sheet of paper, identify all of the good electrical conductors. Okay, raise your hand if you're ready. If you're going to have students call back this, pause the video, but I'm going to go ahead and flip through to the next slide. So if you want to pause the video here and get student feedback, you're certainly welcome to. Okay, so I'm going to go ahead and go forward. So you should have circled all the things that are metal. Metals are good conductors because they have that sea of free electrons. And so electrons can pass easily through because there's already electrons there that can freely move. Air and water can conduct electricity, but they are not good conductors. It takes a tremendous amount of energy to break down the air to allow lightning to transfer. So these are not considered good electrical conductors, but they are electrical conductors. They have some conductivity. Water, we want to make sure when we do safety that we have the area around our electrical outlets dry so that we don't, cause a short or anything in the circuit. So that's another example. Okay? And the rest of these are insulators. Rubber, plastic, wood, paper, glass, styrofoam are all insulators. They slow the flow of electrons significantly in the circuit. And you will be expected tomorrow to be able to pick out from a list which ones are conductors and which ones are insulators. So you need to make sure you've got this down pat. All right, next one. Identify the device. So take a second. We have loads, power sources, and conducting wires here. So take a moment and put each of these in the right spot. So I'll just sort of read this out so we're going along. So you're going to classify a resistor as a load, a power source, or a conducting wire. A car battery, what category does it belong in? An electrical plug and wire, which category would we put that in? Wires, energy efficient bulb, an electrical outlet, a blender, a light bulb, a 9-volt battery, and a toaster. Classify those as either a load, a power source, or a conducting wire. Hopefully you did some of this at home tonight. If we need to, we'll pause the video here for a moment to give students a chance. If you're going to do callback, we want to pause the video a moment and get student feedback or response from this. So again, I'll give you a moment to pause the video if you need to. And I'm going to flip through to the next slide. So a load is just another form of a resistor, something that takes the electrical current and converts it into some other type of energy that we can use. So a resistor, a physical resistor, looks like this. We discussed that that's a long piece of wire that's coiled up. It's really thin. It's coiled up, coiled up, coiled up, so that it provides a large amount of resistance in the circuit. A blender is just an appliance that converts electrical energy as it's going through the device into sound and mechanical energy. A light bulb, which we've used a bunch in class, is just a device which converts electrical energy into thermal energy and light. And these are just resistors. They're just different kinds of resistors. A toaster is just another type of load or resistor that converts electrical energy into thermal energy, heat and light. And then an energy efficient bulb, we don't get as much heat from this, but it does get some thermal energy and electromagnetic energy. So these are all resistors or loads. Power source, that's the source of potential difference, the voltage source in the circuit. What provides that difference in potential energy between the two spots in the circuit so that we can push the current, push the electrical charge through the path. So our power source, we have a car battery, a 9-volt battery. It could be any kind of battery, D battery, C battery, AA. They're all power sources. And our electrical outlet. So remember that our electrical outlet provides alternating current. The electricity, the direction of the charge will sort of swish back and forth. And our batteries provide direct current. The direction that the charge will flow is from the negative terminal to the positive terminal. So we have two types of power sources, DC, direct current, and AC, alternating current. So you'll need to know that as well in here. All right, conducting wires, okay? So we have an electrical plug and the wire attached. Of course, it's metal, and we stick that into the outlet and the charge will flow in one way and back out the other. That's actually how we complete the circuit in an outlet. And then regular wires, it clearly should fall under conducting wires. They're made of metal, and we use those in our labs to connect things. Okay, so moving through to the next one. An electrical appliance has a potential difference of 15 volts placed across it. If the current running through the appliance is 2.5 amps, how much resistance does the appliance have? Okay, so take a second and identify your givens and your finds in the formula. We need to pause the video here. All right, let's go over it together. So they tell me that I have a potential difference of 15 volts. That's my voltage. That's one of my givens. They tell me that I have a current of 2.5 amps. And so that's my current. And they ask me to find my resistance. I'll use a different color. That's this one. Remember, in our formula, we're going to cover up R. That's not blacked out very well. Let me cover it up this way. I'm going to cover up R, and then these numbers are over each other, so I'll get a formula that says R equals V over I. And I plug in voltage in the top and current in the bottom. I use my calculator. Here's the work. I use my calculator, so 15 divided by 2.5 should give me 6 ohms. And remember, that symbol omega is the unit for a resistance or resistor. Okay, next, a battery supplies what type of current when placed in a circuit? 1, direct, 2, alternating, 3, normal, 4, parallel. All right, student answer. Last call for answers. All right, the key word here is battery, and we talked about this just a second ago. Battery is direct current. It flows, the electrons will flow from the negative terminal to the positive terminal in one direction. The current supplied to your house or school is what type of current? 1, direct, 2, parallel, 3, alternating, 4, normal. All right, student response. All right, last call for student response. Okay, so it is alternating current. Remember, this is a type of circuit, it's not a type of current. So alternating current is the most efficient way of transferring the electrical energy, because the charges don't have to move very far. They just kind of swish back and forth in place. We push them right and then they pull them left, and they just move back and forth, alternating direction. And so that's our outlets in our schools and our houses and anything else, okay? All right, next question. Lightning is a prime example of 1, electrical current, 2, friction, 3, static discharge. Okay, student responses. Last call for student responses. Okay, so the answer is number 3, static discharge. I'm going to put it up here so we can see it. Number 3 is the correct answer. Sorry about that. Number 3 is the correct answer. Charge is transferred between the earth and the cloud in a very sudden burst. It's not a continuous flow, so it is a discharge. Real quick, it's over. And we call it static discharge because there's been a charge difference between the two places, and then it transfers very, very quickly. Static electricity deals with that buildup of relatively stationary charges on an object, and then that sudden transfer if there's any kind of transfer at all. Electrical current, on the other hand, is a continuous flow through an electrical circuit. You need that path, like a complete path from one end of the power source to the other. And friction is a method of charging something, so we've got to keep our terms straight. All right, next one. Which of the following are safety devices that are used to prevent a circuit overload? 1, circuit breaker, 2, fuse, 3, both 1 and 2. Okay, student responses. Last call for student responses. Okay, the answer is 3. Both a circuit breaker and a fuse are devices that we put into our circuit. We put these into the circuit in series with the power source, not necessarily with any other components in the circuit, but we put this in series with the power source because if the current flow gets too high, what we call an overload, then these devices will interrupt the circuit. It's kind of like a switch in a way. The fuse has a little teeny piece of metal here that's kind of hard to see in this picture, but if you Google it, you'll see it actually. It's easier in the green one right here. This little loop of wire right here. And what happens is when the temperature gets too high, that wire melts and it creates a gap in the circuit. And we know in a series circuit, if we have a gap or a break, then current will not flow. It just stops. It no longer has a path. A circuit breaker, on the other hand, looks like a little box with a switch on it. And when the current flows too high, the switch actually just kind of flips open and turns off the current. It opens up, creating a break in the circuit, just like the other one. But the difference is this is reusable. So I can go back and I can flip the switch, just like we flipped the wall switch, and we close that circuit back up and it can go again. So one of the key things that you have to understand is this is reusable, this is not. They both are used to prevent a circuit, an overload of the circuit. They're both used to interrupt so that we don't have a fire or safety issue. But that one's reusable. All right, moving on. The following are examples of what type of circuit. So take a look at these circuits. I have 3 very similar circuits. Determine what type of circuit they are. Okay, I'll pause for student response. And we should have said series circuit. Notice there's one path. We can go from the battery through the light bulb back to the battery. From the battery through the light bulb, through the light bulb, back to the battery. From the battery through the light bulb, through the light bulb, through the light bulb, back to the battery. These are series circuits. They're all complete series circuits. Current would flow in any one of these. It says how many paths can current or charge flow through when it goes through one of the circuits above. So I'll pause for student response. And we should have said one path, and that should be clear from the example I just walked through with you guys. Which circuit will have the brightest glowing bulbs? The one with 1 light bulb, 2 light bulbs, or 3 light bulbs? Which one will glow the brightest? I'll pause for student response. And you should have said the circuit with the single bulb. The single bulb has the lowest resistance. Remember when we put these in series that the current actually decreased. Our power source didn't change, but our current decreased and the bulbs glowed less brightly because the overall resistance sort of just adds. We kind of have to go through them one at a time, and so it sort of sees it as one big resistor. If the bulb is removed from any of these circuits, if I just pull one out or a connecting wire is cut, then what happens to the flow of charge? I'll pause for student response. So you should have said the current stops flowing. Any break in this will cause all of the bulbs to go out. Old-fashioned Christmas lights used to be done in series, so it was hard. If you've got 50 or 100 light bulbs and one goes out, then the whole strand would go out and you had to test every single one of them. This is not very practical. All right, next question. When charge flows around a circuit, is it used up and the battery has to supply all of the charge for the circuit? True or false? Sorry, this is a statement. When charge flows around a circuit, it is used up and the battery has to supply all of the charge for the circuit. I'll pause for student response. Last call for student response. Okay, the answer is false. First of all, charges in the wires, those conducting wires have free electrons, and so the charge is already there. And the battery does nothing more than push the charge through and then re-energize it on the other end as it separates the charges. So the battery supplies sort of the force to push things around, but it does not supply all the electron charges. And the charge, as it flows, transfers energy. It bumps into things and it gives up a little bit of its energy, but the charge itself is still there. It's just, think of it as being tired when it gets to the other side. A net electric charge is created by an excess or shortage of electrons. True or false? I'll pause for student response. Last call for student response. Okay, the answer is true. Careful with this one. This is a great test question. And another way of kind of putting it is to test you to see if protons would flow. And we don't ever transfer protons. Remember, the protons are locked in that nucleus, right there in the center, really hard to kind of move around and rip up. And remember also that if we take away protons or we put protons in to the nucleus, we actually change the type of material, and that makes no sense. I rubbed my sweater with a balloon. We know the balloon got charged, but my sweater didn't poof turn into gold. So you have to be really careful of this one. All right. Next question. An electrical insulator is a material that allows the charge to flow freely or easily through it. An electrical insulator is a material that allows charge to flow freely or easily through it. True or false? I'll pause for student response. Last call for student response. All right, the answer is false. An insulator slows the flow. A conductor allows for the easy flow. Okay. All right, a superconducting material is one that is only a good conductor at very high temperatures. A superconducting material is one that is only a good conductor at very high temperatures. I'll pause for student response. Last call for student response. The answer is false. It is a very good conductor at low temperatures. Remember, it was minus 300 and some odd degrees Celsius. It was way, way down there, 10 times colder than dry ice. At room temperatures or higher temperatures, it has a very high resistance. It doesn't allow the charge to flow. Okay, next one. We're told that power output of a device is 12 watts. If the potential difference across the device is 3 volts, how much current is flowing through the device? I'll pause to let students do their own work. This would be a good time if students are not ready to pause the video for a moment, let them do work really quickly, and then pick back up. All right, I'm going to go ahead and walk us through this. So it tells us that the power is, oops, let me change to a different color. The power is 12 watts. So they give us P, and they tell us that the potential difference, which we know is a synonym for voltage, is 3 volts. So they give us voltage, V, and they ask us to find the current. And truly, with these 3 variable equations, if you know 2 of them, you can kind of work out what the third one is. So they tell us to find current, so let's black out current so we get our formula. And so we have I is equal to P divided by V. They're on top of each other. Okay, so I'm going to pull over the work so we can see it. So 12 is our watts. Power divided by 3 volts gives us 4 amps of current, 4 amperes of current. Okay, next one. Identify the type of circuit here. I'll pause for student response. Last call for student response. Okay, our answer is parallel. We notice that this is like a ladder. All of the components are sort of parallel to each other. We aren't going to throw any really whacked out circuits on you for series and parallel. They'll be pretty straightforward, though no, in more advanced classes they won't necessarily. But we can trace it out, and I'm going to wait until after we hit the next question before I trace it out for you. So let's do this one. An electron leaves the battery. How many paths may it choose from as it goes around the circuit? Looking at this circuit. I'll pause for student response. Okay, in this case we have 3 paths, and now I'll draw it out since I did that too soon last time. All right, so I go out the battery, and I get here, and I can choose to go, I go out the battery like this, and I get here, and I can choose to go this way or that way. And if I get here, I can choose to go this way or that way. And so when I go through, then I come back. So I can choose 1, 2, or 3 paths to go through. Now, please don't get confused. This is still a battery, so it is a direct current source. And notice I only flow in one direction. I'm going this way around the circuit, okay? And even, if I look at this middle path, I'm still going that direction, one direction. But there's multiple paths. So it's a parallel circuit, and this one happens to be a direct current source in a parallel circuit. So please be a little bit careful of that as you're doing your test. All right, if we remove the center bulb, this one right here, if we take that center bulb out, let me move it over here so we can see it a little better. If we take this center bulb out, what happens to the flow of charge through the circuit? I'll pause for student response. All right. So current will continue to flow through the rest of the bulbs. We saw this in our animation. I still have a path. I get to this choice, and I can still go this way or this way. And this actually is a complete loop on the outside as well. This juncture is probably a little easier to see for those students who were in the class demo where we did it hands-on, and you saw that I sort of clamped them all together in one spot, whereas the electrical outlets on the simulator, it was easier to make it look more like a ladder like this, but it still sees it as the same point. If you have questions about this one, email me. All right, now we're going to carefully look at each of these circuits and decide whether or not electric current will flow in all or part or some, and why. This is a good point if students haven't had a chance to do this on their own, to pause for a few minutes and let them do this. You maybe work it out together. So if you want to pause here, that's great. And I'm going to go ahead and explain them so we don't have large gaps in the video. So in this first one, it's a series circuit, and with this light bulb broken, we will not have a complete path, so no current will flow. In the second one, this is our simple circuit. Our simple circuit has 3 components: a load, which is any form of resistor, a power source, which is a battery or an outlet, and a conducting wire, and they have to have a complete path. So notice that I have the side of the light bulb and the end, so my filament was in the circuit. Recall my filament went like this, right? It came out from the side, it went up to the top, and then it went down to the bottom. So indeed, my light bulb's in the circuit, and then I'm connecting both ends. I'm connecting the negative end and the positive end of the battery, so we do have current flow. In this one, it's beginning of a series connection, but I have no last piece of wire. There is no complete path from the positive terminal to the negative terminal, so I have no current flow. And then this last one, D, I have the right side of the light bulb connected and the left side of the light bulb connected, but notice that I have no battery here. And so with no power source or voltage source, I cannot get any kind of current to flow. There's nothing that's going to happen there. Okay, then on E, let's take a look. So we come out of the battery here. Uh-oh, I don't have that other end of the filament attached. Recall that the filament goes up like this and comes down like that. So the light bulb is not in the circuit. So actually this should not say no complete, no current flows. Let me fix this. It should say current flows, but not through the bulb. This is a short circuit. Current will flow, but not through the light bulb. So this one's, the answer is a little bit off. So the light bulb will not light up, but current will flow. This is one of those circuits that we say is really dangerous because there's no usage of the energy anyplace, and so we're just pumping it back into the battery and the battery overheats. This was our short circuit, okay? On F, you can see there's a gap here in the wire, right here, there's a gap in the wire, and so no current will flow. The bulb is in properly, but no current will flow. Okay, and this one, again, notice that my negative terminal is not in there, so no current will flow. All right, on this one, let's check here. So I have that end, and I have this end, and I go to the other end. So yes, series circuit, complete, simple series circuit, current will flow. Okay, and on this one, I follow out from the battery. I can go this way, and that side is complete. So that's one path that works. This is a parallel circuit. I go here. Nope, there's a gap in the path. This one will not work. But I can go this way, and that is a complete path. So current will flow, just not through the center bulb. And then the last one, we see that the open switch is here. So we have to trace it back out. As I go out this way, I don't have a path to go for. So I can't, this is a parallel circuit, and we have a break, but the break is next to the power source. And with the break next to the power source, no current will flow. That's why we put our fuse and our circuit breaker in series with the battery, but not necessarily in series with anything else. If there's an overload, it just shuts the circuit down. And one of the things you should have noticed in the lab is as we do parallel circuits, it effectively actually reduces the resistance in the circuit because now you have more paths to go on. You can think of it like traffic around the beltway. If there's only one exit or there's no exits, then all of the cars kind of get on and then get backed up. But if there's lots of exits or lots of lanes, there's lots of paths for them to go, and the traffic tends to be a little bit lighter. There's less resistance, the cars can go a little bit faster. So that's the analogy to help you with that one. All right, so this is a good place for the teachers to kind of pause and go over some of these extra reviews. I have posted these links in a document on Edline it's under the calendar, it's also under your homework link, so that you can practice. There are 3 Jeopardy games. There's a Quizlet. There's 2 Quizlets to test your vocabulary. One was practicing your circuits, what lights up, what doesn't, what has current flow, what doesn't. And one does vocabulary. It's not all of the vocabulary for this unit, but the teacher who created it did a really good job of hitting most of it, so it's a good resource. And then we still have our 20.1 quiz review. So these are kind of a mix, but if you need more practice with that static electricity, because that's older, then go back. I also have tucked on the end some vocabulary practice. We had talked about graphic organizers and categorizing some things. These are good ways of kind of categorizing that for your practice. The last very sheet in your packet is a copy of a study guide that was given to the other class, and if you need answers to that, you can send me an email, or I will try to get that posted later today. All right, good job, guys.